Hello everyone. Today we'll discuss about the CodeChef Starters 91. I'll be explaining all my 5 solutions, the solution of the first 5 problems, and we'll discuss a little about the limited shopping and more inversions. So let's begin. First is the odd GCD permutation. So let's read the problem statement. Firstly, we are given an integer n, then a permutation of integer n. If the permutation of n is numbers from 1 to n arranged in any order such that the GCD of the numbers at odd indices is greater than the GCD of numbers at even indices. So firstly, let assume the k is the GCD. Let k assume the GCD of the n by 2 numbers either at odd indices or at even indices. Okay, so this k, for this k to be a GCD, we should have numbers k, 2k, till n by 2 into k within n, that is it should be less than equals to n. So if this is less than equals to n, we'll get k is less than equals to 2. Okay, so either 2 can be GCD or 1 can be GCD. Now considering this, since the GCD at odd index has to be greater than GCD at even index, so the GCD at odd index has to be 1 and even has to be 1, so that it is greater than even indices. So let's assume for it odd indices to be have GCD 2, we have to give it numbers like 2, 4, 6, 8, and for odd indices 1, 3, 5, 7. This is the only option. Now if you see, if we end it at even number of indices like 4, 6, 8, then it will have proper answer. But if we end it at 3, we can't get a permutation. So at n is odd, we won't have any solution. And when n is even, we can just randomly put any even number at these indices. What I did is just put them in reverse order, because since n is even, the first number would be even, then odd, and like that. So here is my solution. I check if n is odd, then C out -1. Otherwise, I just print in them in reverse the order. You can print them in many such orders, no problem. Let's move to problem 2, which is chef odd. So we are given a set from 1 to n, and we have to divide into k sets such that each set has a sum greater than 2 and the sum of each element is odd. So if you look carefully, we have n numbers from 1, 2, 3 till n, and we have to divide this in k. As you know, initially sum is even. Let this be k. Initially the sum of all is even, and we have to get a sum out. So we'll call this as a false state. We'll call even as a false state and odd as a true state. So initially all are at false. So if I add odd number to any of these states, like odd plus even will still remain odd and even plus even will still remain even. So we can say even number does not matter. So now I have to change the states of these by putting odd numbers in each of these. So I'll put one odd number here, one here, one here. So k odd number will be used. So there goes our first condition. We have odd numbers is greater than equals to k. Okay, after that there is, suppose we have r remaining odd numbers, but if I add any more odd numbers, the state would change from true to false again. True to false, but I have to use all the numbers. So if I use, suppose I have already used k, if I use one more, the answer would be false. But if I use 2 more, I can change this false state back to true state. So means if I have k number of odd, then it has answer k plus 2. Similarly, k plus 4. It means if the number of odd has same parity as k, number of odd has same parity as k, then then we have an answer. So I just did that implementation. So firstly, there are two conditions. First is number of odd number is greater than k. This is that condition. Okay. And the second is the parity is same. If you the n plus 1 by 2 is the number of odd numbers we have, and its parity, that is modulo 2, is same with the case modulo 2. Then answer is no. If it is same and it is greater than n, then answer is yes. Okay. Now moving on to our third problem, which is maximum sum permutation. In this, we are initially given an array of size n. Then we are given q queries and ranges from L to R. So what we have to do is we have to sum all the numbers from L to R in the array, and with that sum we have to add this to some number x each time in each query, and we have to give the maximum possible output we can get after performing all the queries, and give the order of the array. So what we can do is we can change the order of elements in the array A. So we have to change the order in such a way that we get the maximum output, and then we have to print the changed array A. So firstly, in this solution, I'll just start some very basics. How do you perform sum from range L to R? What I'm trying to do is I'm trying to count how many times each number is summed in the answer in total. Okay, let's these be indices 1 2 3 4 5 6 7 8 and 9. Let's assume we are given the query 3 to 5. Okay, what I'm doing is I'm adding 1 to each of these. It means 3 has come one time, 4th index has come one time, and 5 index has come one. Let's give it another query 5 to 7. I'll change this 5 to 2, 6 to 1, and 7 to 1. So now after all this, I would know that 2 has come, the 5th index has come the most time. So I'll put the greatest element of the array here, and similarly in same order, like if it is 3, it is 2, it is 1, greatest here, second greatest here, third greatest here, and so on in that order. So but we can't put L to R every time, so there is an efficient method to do this. So how do we handle these queries in big O of 1? So what we do in such queries is we just put ones at the beginning and at the index after the last one. Here we'll subtract 1. Now you see, if we perform prefix sum, it will give 0 0 1 1 1 0 0 0 0, which is our range. If we do this for this query as well, let's put 1 here and minus 1 here, and if we perform prefix sum, we'll get 0 0 1 1 2 0 2 1 1 and 0, which is what we would get either way. So we can handle these queries in big O 1. So now we have gotten how much times which number we have get. So according to that, we can sort the array. First we'll sort the array, so we'll get the greatest number, second greatest, and so on, and we'll put them in the order in the most time they have come. Like at which index the maximum has come, we'll put the maximum element of the array there. The second maximum, let's say this index has come the second most time, we'll put the second greatest element there, and so on. So I'll show you my implementation. So So first I take the input and sort them in decreasing order, and this array name dp. In this I did the work I shown you here, the plus and minus one. I just plus the L and decrease at R plus 1. I'm using zero based indexing, that's why I've used L minus minus here. So after that I've performed prefix sum that I told you. After that I have pushed this in an answer array. So in the answer array, actually the value and the index is stored. So I can sort them according to the value, and I'll get the index which appears the most. So I've sort the answer in the decreasing order as well. So uh, and this is the counter which is my the array I am going to output. Okay. So what I am trying to do is, firstly I am putting the greatest element which is a0 at the index of answer 0 dot second, means where which element has occurred the most time, which I am implementing using this. So as we know, answer I dot first has it's the amount the greatest index at occur, the ith index has occurred, and this is the value. Okay, then I stored it in the answer and then output these. With that, let's move on to the fourth question, which is XOR and sum. So in this problem we are given two numbers L and R, and we have to count the number of non-negative integers such that there exist a and b which satisfy the following requirements. X is a or b, and it is also equals to a plus b. Okay, so let's discuss about some of the properties of XOR. Okay, if a plus b equals to a XOR b, then we can say a and b equals to 0. A and b is equals to 0, because if there would a bit that will be present in both a and b, okay, then in XOR it won't occur, but it will occur in a plus b, so they will not be equal. Let's assume the range 1 2 3 till some x, some y. Let's assume this x, okay, is some 2 to the power k. It is 2 to the power k. It is the highest 2 power of 2 which is present in this, okay, in this L to R. So every number after x plus 1 will be 2 to the power k plus 1, 2 to the power k plus 2, plus 2 to the power k plus y minus x. So in these numbers, if you see, if I take any two numbers, okay, if I take any two of these numbers, you will see their end won't be equal to 0, because 2 to the power k, the k plus 1th bit or kth bit is present in each of these numbers. Okay, so I can only pair these numbers with numbers lesser than these. Let's assume these numbers to be, let's say, 4, and this number is 5, 6, 7, and let's say this is 3 and 2. How many can I pair with 4, 5, 6 or 7 to get distinct answer? If I pair them with 4, you'll see we'll get 6 and 7. If I pair 5 with 2, I'll get 7. But if I pair them with like if I pair 5 with 3, we'll get a conflict of 1 bit, and with this I'll get conflict of another bit, with this I'll get conflict of both bits. So you see, the result won't change if we only use to pair them with 4. So you can we can say The number less than 2 to the power k, we can just pair them with 2 to the power k if k is the highest power. Let's move on to the. So what I did is I did the answer for all the powers 2 to the power k, then for 2 to the power k minus 1, 2 to the power k minus 2, and so on. But there was an edge case. Suppose in this you can 4 cannot be paired with 4 either, okay, because they have a same bit. But suppose if I say x plus x equals to x XOR x, as you know x XOR x equals to 0, and x plus x equals to 2x, 2x equals to 0, x equals to 0. This is an edge case of the problem, because if L is equals to 0, we'll have to add 1 to the answer. So we can say the logic is pretty simple, where we just follow this algorithm 2 to the power k, 2 to the power k minus 1, and so on till the lowest power of 2, and just add the number of numbers behind them. Let's say this is it starts from L to x. So now I'll show you my implementation. Okay, so I just chose multiplied k by 2 until I get the until it is greater than r. So I get the highest power of the. So I'll get highest power which will be stored in counter. Now I know this counter is greater than L because it is the highest power. So after I've gotten the largest power counter, I'm iterating to the lowest power dividing by 2, and each process adding it to the answer, and then I'm handling the edge case. If the lower limit is 0, then incrementing the answer by 1, then outputting it. Let's move on to the fifth problem, which is the cheapest office. In this problem, we are given actually n rooms, and there are m bidirectional passages assigned to these rooms. In essence, we can actually call it a graph with n nodes and m edges, uh, and with each node having a cost ai. So we are given an array A in which we have given the cost of each nodes. But in the problem, we have to select can k rooms such that they are connected. They are connected. K such rooms that they are connected, and we have to minimize the or minus and of these nodes. We have to minimize or minus and of this node. Uh, so let these be some nodes which are connected to each other. Let these be k nodes, and the end be a and or be o. So we have to actually give the answer of o minus a. We have to minimize it. So for this I used an algorithm which I like to call the bit search. In it we search if a particular bit is present in the answer or not. So since we iterate from the highest bit to the lowest bit, right, from the 30th bit to the 0th bit, if it is present in the answer or not. Since we want to minimize it, we'll take if there is even a single case where the bit is not present, then we'll choose that case. The bit search is essentially a binary search, but the constraints are from 0 to 2 the power k minus 1, just 30. But we iterate bitwise rather than just choosing a midpoint. It is essentially the same. So what I'm doing in this problem is checking if each bit is present in the answer or not, and then modifying the tree accordingly. Let's suppose this. I'm checking for the kth bit, and this is the current tree. Okay, and these three nodes have kth bit, and these three bottom node does not have kth bit. Okay, and the question k given in the question, let it be 3. So we need to find 3 connected node, one which we can find here and one we can find here. So there is an answer possible. Okay, so since this answer is possible, what I'll do now is break these edges. So what will happen will, in further iteration, will never go to a case in which the adjacent node have one has k bit and one doesn't have kth bit. One has kth bit and one doesn't have kth bit. So that kth bit will never be an answer. So I'll show you my implementation and I'll explain accordingly. So I iterated from the uh, uh, in the e question. Firstly, yeah. So NMK input, A input, the cost array, then adjacency list. I use as generally use zero base indexing everywhere. Then I iterate from bit 31 to bit 0. First is the boolean k, small k. What I am using it for is if there is a single answer possible or not. There is a visited array and there is a DFS function. This DFS I am using to check the k connected nodes. If I go from here, how many nodes will I visit in this iteration will give me how many connected components are there with kth bit. Suppose I'm BFS using BFS from this, then I won't go to this node. I want this considered as an edge. So how I'm doing that is in the BS function. What I'm doing is, okay, for each edge I'm checking if the node is visited or not, obvious, and if the XOR right shifted to the bit and one is 0 or not. If the bit is present in both of these, then the XOR would be 0. And if we right shift it by bit, then obviously since that bit is 0, it will give 0 and 1 will give 0. But if one has this is 0 and this is 1 and right shifted by bit, then it will give us 1 and 1, which will be 1. So if this is equals to the 0, then only I am considering it as an edge. And now after this I'll just perform BFS if the node is not visited for each node to check if there is an answer. If there is no answer, unfortunately this bit will have to be in the final answer. Counter is my final answer. Okay, I am changing it every after iterating with every bit. Okay, so this will be present in the answer. But if this bit is not necessary in the answer, if even there is a single case possible, what I'm doing is I'm making a new adjacency list in which I'm not adding those edges which have their and 1 equals to 1. I'm only adding edges which have their and the XOR with 1 is 0. You understand what I'm trying to say? Just the bit is either present in those both or not present, then it is only edges. So I'm just deleting edges from the graph in each of my iterations. I've seen the implementation of many people and they've used DSU. If either two components are part of the same DSU, then there is an edge between them or something like that, though that doesn't really matter. Okay, so this was it for the fifth question. Now let's move on to the sixth question, which is limited shopping. I didn't solve this completely, but I did two subtasks. Um, there are shops from 1 to n. Basically, we are given an array of n with value vi each, where vi is the value of each value of the array, each element of the array, and we can choose every number nami number of times. But if we want to choose it nami number of times, the previous we have to choose the previous element at least nami minus 1 times. We can just get the one on left side and achieve that, no problem. And similarly we have to find the maximum and the number of times we can take an element. The sum of that should not be greater than k. Okay, so I've used dp with parameters 3D parameters I, J, and K, where the first will be the index, and which will have a constraint from 0 to n plus 1, and the number of dollars, the money I have used, and the current num. So initially I used minus 118. So what I am trying to do in the DP is, for this particular index and this number of dollar used and this number, what is the maximum value I can get? That is the DP I am trying to use. Initializing the DP000 by 0, I am iterating from index 0 to n for each dollars I have used, and then what would be the num at that for each num, what is the maximum possible value we can get. So uh, the DP it's in itself is pretty basic. Suppose I want value from I, J, and K. So ith index, so we only have to take account in the I minus 1th index. If J is the number of dollars I am using and K is the num here, okay, so that means I must have spent J minus K dollars till the last, till I minus 1. I would have spent J minus K dollars, and num I, this here, would be greater than equals to K minus 1, K minus 1 to, let's say, n. Okay, as num I can never be greater than n. So if we try to implement this, we will need, for each I, J, and K, we will need to iterate to this. So it will take big of n cube into K. That would be sufficient to do the first subtask, but it would fail in the second subtask. So let me ask you, if I was taking answer for I, J, K plus 1, I, J, K plus 1, what will I get? I minus 1, J minus K plus 1, um, uh, mm, let's say, no, rather than changing the J, rather than changing the yeah, with same number of dollars rather than we have spent, we should change our way of looking at it. You can see here, what I am doing is, for each I, J, K, since we have to always check for K to n, K minus 1 to n, so I'm not just storing K minus 1 here, I'm storing the maximum of K minus 1 to n. So it means at I, J, K, the answer stored will be I, J, and for this parameter it would be maximum of K to n, because if I want to check for K, I'll always have to check for K to n, all the cases from here to here. So if I do this, I can just optimize it by using this implementation, iterating it in reverse. Iterating in reverse, I can the above value will already be computed, and from that pre-computed value, I'm technically taking a prefix maximum, you can say, of the current value and the previous values, and I'm getting my answer from there. Okay, after that I check answer for each for the nth index for each value of j and k, and I have output the maximum answer. This would be enough to fit a complexity of n square k, but in the answer we can't use this complexity for the subtask 3. So I did figure out a way of you can say optimizing it, because if we look at I, j, and k, okay, for each I can say that k is always less than equals to I, because to if I want to get to a particular num, it will have to be 1, 2, 3. Okay, so for third, num cannot be greater than third no matter how I increment it. Okay, so first is this condition. Okay, the second condition is the number of dollars I spend. Okay, if I am at num k, Okay, I have used $1 somewhere at num1 and num2 some $2. So if I am at k here, I must have spent, okay, k into k minus 1 by $2 somewhere, which can optimize the complexity. We can optimize the space complexity as well as time complexity to think about. Oh, uh, okay, um, I and k are together and j is kind of separate, so you can say big of n k root k type some complexity we can get. And we can't allocate a 3D DP. We'll most likely be allocating something like a map, I think, I assume, or something of a pairs or something of that sort. So that's it for this video. uh, I might discuss another solutions next time. See you, peace out.